This conference will now be recorded.
Sounds good.
So thank you, everyone. Good morning, good afternoon, wherever you are joining our session today. We will start with the agenda. So for today, what we had planned out is continue with the technical discussions. The first one will be with Gary from SciTime, who will spend with us time on the 1588 solutions. It will be about 30 minutes that we have planned.
Actually,
Gary, are
sorry,
you
can we change the order a little bit because Gary is running a little bit late. He is starting
sure?
a previous meeting. So if
no
you could
problem.
change the order, please.
Of course.
Thank you.
So we'll start off with Oleg, Facebook's and the workstream leader for the Open Grandmaster, who will give us an update about the workstream. It's about 20 minutes. Then we switch to Gary for about 30 minutes, and we'll close off the call with a preview of the upcoming OCP Tech Week, which is happening for us on November 12th. And some updates from us on tap, and I guess the OCP may add other marching orders. Does that sound good to everyone? All right. So Oleg, over to you. I'll give it the screen.
All right, thank you. Let me just quickly figure out how to share the screen. Okay, do you see my slide?
Yes. Yes.
Okay, yes. So forgive me my drawing. It was very schematic and yeah, maybe even last minute drawing. But anyways, I just wanted to visualize what I'm going to talk about, so it's going to be much easier accepted by people looking at this presentation. So, okay, we have so-called concept of Open Grandmaster. Yeah, hello again. My name is Oleg. I'm production engineer at Facebook and leader for this direction of the Open Grandmaster project, of Time Appliance project. So basically, first, I probably need to mention the problem. So the problem is obviously different vendors have different solutions for such for the Grandmaster or NTP Stratum 1, as you may call it, and they sell you different hardware, which usually comes with their own software, which is always pain, and it's really hard to ask for new features, etc., etc. You're all familiar with the drill. So we are working on basically building a specification for the Open Grandmaster, and this is how we think it's gonna look. So the typical Grandmaster you can break into smaller pieces. Obviously, it's not one huge monolith. So in our case, we decided to go with a couple of pieces, and I will go through each of them, and then also explain how they interact with each other, and then give word maybe to Ahmad and Dotan, who will tell a bit more about them. So yeah, what's Open Grandmaster? It's basically a regular server, nothing special. It's a regular server with open source software on it and with some a bit customized hardware. So in our case, like you can see on the screen, we have this block is a server. This is the line which is a motherboard you can call, and there are two, for example, PCI Express. At this moment, we're thinking about PCI Express, but it's not set in stone. So, and it's obviously not mandatory to use exactly PCI Express, but for now, we're talking about PCI Express. So then you have a network card connected to it, which is obviously performing the role of the Grandmaster. You cannot work without the network card, so you need a PTP or NTP to basically to communicate over the network packet protocols. And of course, this network card should have hardware timestamping support, and it should have extra interfaces on board, which should facilitate our Grandmaster. Then you have a second card, which we call a time card, which is a special piece of hardware, which we're working on designing the specification right now and building a test implementation. So it will consider, it's again a PCI Express card, so it will have atomic clock on board or any other clock which can perform a long holdover. It has the GNSS receiver, which basically source of time where it comes from. it will have a bunch of ports. We are thinking about SMB ports just for simplicity, and those this will be like PPS input, PPS output, 10 megahertz input, 10 megahertz output, for example, and there will be FPGA on board, which we will talk a bit later about. So those two cards and the server, like physical hardware, and some open source utils like PHC2Sys and then Crony or PTP4L is a foundation for the open source Grandmaster. So by having those components, you can have and you can build your own Grandmaster instead of buying ready solution from the market. So if we go dive a bit deeper into the responsibilities of those components, so the network card has PPS input and output for precise synchronization of time. It might have PTM, which, because it's using the PCI Express, will greatly improve the precision. Then it should obviously have hardware timestamping for the NTP or PTP. And it should have an interface, because it's connected with PCI Express, it exposes itself as the hardware PHC clock. So it will provide time of day. So usually it's def PTP 0, for example, on the Linux, and you can read time of day easily from it. So the time card side, it must perform a holdover. So that's why, for example, here is atomic clock. It has a GNSS receiver to get time. It has a FPGA to handle basically being a bridge between the GNSS and atomic clock, perform some functions like leap second not smearing, but propagating. And also it should also expose itself like a PHC. So it should have an interface to get and maybe even set time of day externally through open source utils. Okay, so now we more or less figure out a general picture how it looks like from outside. Yeah, so the idea is that this setup is easily buildable. Like anyone, my favorite example is a research in Siberia. If this researcher doesn't have money to buy a very good, expensive network card, for example, which, for example, doesn't have a PPS in, right? So they still can enjoy open source tools like PHC2Sys to copy data from time card to the network card. There are open source software which handles this, and they still enjoy not extremely precise, but pretty good precision, which is fine for research purposes, maybe for development of software, for many other markets. So it's basically a long tail of markets will be covered just by using the software copying of the clock. And if you want extreme precision, like we, for example, do, you just have an extra cable which copies PPS output of the, which leads the PPS output of the time card to the PPS input of the network card, and this brings the precision to crazy numbers, and we expect them to be less than 100 nanoseconds. So yeah, we went through responsibilities. So then we go a bit deeper into the specification. As I mentioned already, the time card itself should expose itself as def PTP as something. There should be open source tools like PTP4L, easily working and accessing this information. And additionally, yeah, so this should provide the precision around less than 1 microsecond. And if we want extreme precision, we plug 1 PPS, and it gives 100 nanoseconds, under 100 nanosecond precision. So in our experiment, it's actually a single or maybe double in the worst case digits of nanoseconds. So, right, this is about time card. One of the inspirational examples might be the card from Microsemi, which they were selling some long time ago, but it doesn't have many features which we actually discussed right now and which we are mentioning. So that's why we cannot use it, for example. Right, so obviously the GNSS receiver could be just purchased anywhere. It's uBlock. Yeah, nothing super special about this. It should just provide several interfaces, like it should provide time of day, it should provide 1 PPS, etc. And for the holdover, so there will be atomic clock or any other substitution of maybe even very good OCXO temperature compensated, so it should be fairly pluggable. It should be abstract. Like we should have abstraction from it. And yeah, so the bridge I mentioned could be built using multiple ways. It could be so-called software bridge, where the software does the job. Then it requires GPSD and etc. This is like just in case approach. We don't want to go with it and don't want to spend too much time on it. We're thinking about hardware approach, so hardware bridge between atomic clock and GNSS. So our sketches look more or less like this. We have some metaphorical PCI Express card with some outputs and inputs. Then you have a Rubidium clock, for instance. There is a PGA. You will plug it in. And this is basically add-on to have a really great precision. So there are some interfaces described here. So it should have, in our case, we go with PCI Express, PPS in out, SMB connectors, GNSS antenna, and yeah, it might be actually, if we merge functionalities of the network card, it might be actually having network port as an optional add-on. Right, so it should have LEDs to signal the status on it, obviously. And yeah, this is a deeper dive into the how FPGA works. I don't want to stop too much on this at this moment. Right, so the software running on the server, which will facilitate everything working and as expected, it should be a standard Linux or Unix, like descendant of Unix operating system. It should be visible, so there has to be a small driver, which we will use something very generic, which can expose the registers of the time card and map them as a PTP device. And PPS actually as well. And yeah, so this is very small. We had, so the need for it is because there are custom registers depending on what FPGA is used. So you have to have those registers written somewhere. So yeah, PTP4L is running, and it's using features of the network card like hardware timestamping, etc. So for NTP, it can be used Cronny, for example, which also can read the FPTP device to become the NTP server. And the network card's requirements we already mentioned. And one of our, we work closely with NVIDIA and Mellanox. So we are talking in this case about Connect 6 network cards. Right, so with this, I can give a word to Dotan, who can tell a bit more about the network card component of this setup.
Hi, if you can leave the slide on, I'm going to talk about this slide.
Oh, okay, sorry.
So I want to explain another huge motivation that we see with that open design. I mean, essentially our goal and aspiration is to introduce time sync service into a data center, to make it commodity, to make it ease of usage. Oleg mentioned his friend at Siberia, and we all have friends. Time sync is not something that is easy to deploy in data centers. It requires all the operational infrastructure to be cooperative. Now, when it comes to Grandmaster, this Grandmaster contains networking functionality, it contains accuracy functionality, and it contains what is hidden inside the PTP profiles, which is industry specification for packet format, for specific points of accuracies and cost, etc. And with that design, I think we divide those three components, and we just ride on the commercial trains that go as fast as we can. So the network cards, most of the network cards today provide hardware timestamp. Indeed, Oleg mentioned our adapter, but if it was our adapter that provide only our adapter that provide hardware timestamping, we wouldn't have done this. This is becoming a commodity. Network cards support hardware timestamps. So when the benefit from using a network card with that functionality means that your grandmaster is completely agnostic to the, for example, to the network speeds and feeds. You're gonna upgrade your network into 100 gig, that's no issue. Just replace the network card. You're going to introduce new PTP profile that require a different packet format. You don't need to change your grandmaster. Everything is open source software. You want a different point of cost and accuracy. You want a TCXO instead of an expensive atomic clock. Go ahead, replace your timing card. So each card, each element in this system represents something that is aggregated as unique and sorry, not unique, as a monolithic point of interest. So the timing card is responsible for the accuracy part. You can design it whatever you want. You can design it to be cheap with a single GNSS receiver and a TCXO. You can design it to be like a very fancy one, like multi-constellation GNSS with an FPGA and atomic clock and whatever you want. And you can have your own network card. And of course, software will deliver every PTP profile next to you. You can examine new filters to accommodate noise. All those fancy articles in the academy about filtering network noise, lucky packets, all those things, they will be much faster deployed in such architecture. So with that, I will jump in just for a few minutes about how do we going to do that with our network card. Actually, it's pretty easy. We have an internal clock inside the NIC, of course, otherwise we cannot timestamp. Every time we get a PPS pulse, we snapshot the internal clock at the PPS signal arrival, and we send it to the software. So software get a message like, you got a PPS in at 8 o'clock and 200 nanoseconds. Okay, software can save that. And then software can get another PPS in. You got a PPS in at 8 o'clock and 1 second and 300 nanoseconds. And later on, software can decide if she wants to readjust the clock by 300 nano to adjust the frequency, to ignore some of the sampling because they are outliers. This is completely algorithmic part. What we deliver the accuracy. We deliver the timestamping. And once the servo is closing the loop with the NIC, that means that the hardware timestamp on the packet themselves are much more accurate. And we already demonstrated in lab. And I do expect us to show that in OCP Tech Week. So with that, I mean, there is a huge motivation for network card to continue and evolve. So we are riding on that train. Network card will support multi-host, will support more OSs, by the way. Once Windows will allow our timestamp to run through their OS, it will be like a few days later, and this design could fit in also in Windows, which is sound unbelievable now.
So one thing I wanted to add with respect to the timing card. So we're taking two approaches. One is like, first of all, like we're opening the design as much as possible, and we have like a suggested block diagram. Or like, would you please like scroll there? So I make the suggested block diagram is, I mean, it's pretty much like bread and butter when it comes to, like, I mean, this is the schematic we're assuming, but I mean, things can change. We're just giving like a suggested thing, like where basically the FPGA is acting as a bridge to communicate via PCI Express. You have GNSS and Rubidium clock on two sides, and then you basically have the 10 megahertz like input output and the PPS input output. So both can be like presented in front of the card or with a SMA connector or like an IPX connector on the board if you want to keep everything inside the board. So let's scroll a little bit down. So in terms of like the block diagram, overall block diagram, what we're going to have in an FPGA, we're thinking like pretty simple. Like we have basically the bridge showing up here. You have a PHC with a GPTP protocol 80 bits, and then you have the DPLL. For example, we're talking with some other colleagues, and the idea of like putting an external, let's say, PLL that you feed it basically, not a PLL, basically externally creating the PLL with a VCO, and you feed the VCO, let's say, with a high precision DAC, and you feed that thing back in. I mean, this is just a suggestion, you know, and then we're gonna have for this quote unquote suggestion also, like in the same time as we develop the hardware and like what do you call the FPGA code and IPs and everything, we'll also develop the PCB for it. Like we'll have like the BOM and the schematic available as we go through. And then let's go next. Or like, so basically what it boils down in is like you have the atomic clock or OCXO, you name it, or you have cesium clock or hydrogen maser, whatever you have. You feed that thing in, you have your counter. Your counter is supposed to take basically the 1 second. You compare the 1 second that you get from your counter with the 1 second that you get basically, or like, let's put it this way. You have a counter that is running the beats with your atomic clock, and you're taking snapshots from the GNSS that you get in. And then you see how far they are from a second. And then you use this back to basically tweak your VCO or again, PLL or something. And this is basically called disciplining your oscillator. And then once your, let's say, GNSS or GPS is gone, you can heavily rely now on your atomic clock that you already disciplined when in the presence of the GPS, and you can continue on. And then you can provide like all sorts of like, let's say, control schemes here, more aggressive or like soft, or like it really depending on the application. Or let's say, for example, an application would need more reliability. Sure enough, just add another PPS input, like, or like another GPS GNSS receiver, and now you have like redundancy. You can add a second atomic clock, let's say, and you can have redundancy more on that side. All these like ideas, we want to have, let's say, something for them that you can basically either tweak or even like more like a off-the-shelf hardware you can take in and continue from there. Oleg, I leave it to you to continue.
Yeah, that's actually summarizes it very well. Right. I don't even have much to add, to be honest.
Sure, let's hand it then to Elad.
Can I have a question then?
Oh, good,
Sure.
good.
Yeah, I mean, you were showing the block diagram of the FPGA, and so as I understand, your most basic approach is to just adjust the counts. So when you're you're comparing GPS signals from with the rubidium with the atomic clock, and then you adjust in the most simple version. You adjust the count in the digital counter, and then you're limited by the basically the resolution of the counter of your internal FPGA clock. Let's say if you're running at 400 megahertz, you're 2.5 nanosecond resolution. And then you're suggesting
not like that. If you look at the design, we take the 10 megahertz, we jack it up with a 12.5x PLL, we go to 125. So 125, screw the next slide. So on 125, we will basically have the 8 nanoseconds. That's the standard beat for basically the PPS. And then you have that counter that starts counting, and you basically are waiting to see how off it is from 1 second. You reflect that back because the GPTP is 80 bits, 48 bits of it is seconds, and 32 bits is subsecond. 32 bits means 250 picoseconds. 8 nanoseconds means like you're 5 bits further from the LS bit. So it gives you 5 bits of changes. That's your resolution of adjustments.
Yeah.
That's not enough, no problem. We're putting we put a DAC, let's say 14 bits DAC that feeds a VCO. The VCO feeds in now your beat, and now you have like it will be like 16,000 steps basically that you can adjust your beat, which is again 8 nanoseconds. And we're sticking to 8 nanoseconds because we see like this is basically what is used more in standards. Like also like let's say in the like the clock input for the FPGA, we're open to anything else.
Yeah, it's just very interesting because we had, I mean, we had a lot of discussion about the FPGA, and we had a lot of discussion about the FPGA I mean, I've encountered one of the requests because we do have TCXOs with digital control interface, and one of the 1588 vendors, basically companies that deal with 1588, they wanted to use our parts to digitally pull the oscillator with fine resolution and improve their adjustment resolution from, I think they had 4 nanoseconds, and they wanted to drop the discrete step and go with much finer resolution.
Absolutely.
So that's why it triggers the interest. How you're
So we can actually continue. I see Gary's here, and like the SI time folks.
So this is Alon. I do have a question, if you don't mind, before we switch to Gary.
Right on.
And this is just trying to understand how this meets as I remember from previous meetings, one of the stated goals was to be able to synchronize a data center so that across all virtualized machines, everything will be within 10 nanoseconds of each other.
10 microseconds.
10 microseconds, okay.
Yeah, 10 nanoseconds.
That's what I remember being said in one of the meetings.
So for 5 nanoseconds was the budget. We broke it in 2.5 in an arbitrary, basically taking 2 arbitrary machines in a data center. You should have 5 nanoseconds with each other, and that is all driven from, let's say, the shortest latency you get between packets. And this requirement's, again, not set on stone. It's gonna get basically tighter and tighter as we go further.
So
you mean microseconds, right? How many?
Yes,
you mean 5 microseconds?
5 microseconds, 2 arbitrary machines, meaning from the grandmaster to every machine you have 2.5, and then we broke it in a budget.
As long as we're in microseconds, that's fine, and we're not in nanoseconds, because I heard nanoseconds one of the meetings, because then I was going to comment that you're going to have a hard time with this design, but microseconds, no problem.
Yeah, microseconds. However, we are extremely sensitive on the like the error, basically the reliability and the error budget. So the error budget, it's like basically we need to see like what's the error bound, how much, like, okay, you tell me this is, let's say, I don't know, this is the time, how much can I trust it 100%? I mean, you get it like that, 6, 7 nines or something.
So you can think of it like a tower, okay? The main floor is the clock within the network adapters. They will be more accurate than few microseconds. Then we will synchronize with them the system clock, which will have a bigger noise. And then the application error bound will be slightly bigger than that, and it's supposed to be perfectly bounded. The time that Ahmed mentioned is with respect to the application error bound.
Yeah, exactly. And so you've budgeted out into various parts of the network, which is fine. Again, I
think it's worth it to mention, Alon, like the most important thing we're looking for here is called linearizability. And I think you're familiar with it, but to the others, linearizability comes when you can have an accuracy in your clocks better than the network latency. So in NTP, because your clock, the mechanism is so that the clock is delivered over the network latency. I know you have like RTD compensation methods or something, but you have the variance because you don't have hardware timestamping. You will be limited to the network latency. So because the network latency, your clock is not more accurate than the network latency, you no longer can just rely on committing on 0 weights, and you have to have always this weightings that they will make sure that your, like, let's say, received timestamp is linearizable. It means you never receive messages from the future. So that is basically the whole concept of like why we're going with this whole, again, like we diverge a lot, let's say, from open source Grandmaster to the fundamentals why we're doing this.
Thanks, Ahmed.
Ahmed, I have a question. Are we going only to use NTP for clock transportation, or will we use the 1588? In this project, the clock is.
This project is about the PTP, NTP, but we don't want to eliminate NTP. We want to keep NTP for whatever it's right now doing. Backward compatibility is also one reason. But I'm fundamentally thinking we don't even want to change actually the system clock with the PTP. Like we want to keep the system clock running on NTP. PTP, on the other hand, will be available there, and then we have like some like nice methods right now, basically to propagate now the clock all the way from the PHC to execution of algorithm, like basically different commands, to have them accurately, let's say, mapped with that accurate time that we're getting from the PHC. Let's table all these discussions because we have Gary and the sci time guys. So let's continue with that one.
Yeah, that's what I was going to say. From the time point, it's time to move on. If there are any further questions, please write it down and we will address. Gary, would you like to go ahead and take the presentation?
Sure.
So I made you a presenter. Thank you, Oleg. Thank you, everyone.
Okay, I think you can see my screen. All right, so it looks like a nice discussion you guys had. I'll have to go back and view it in the video, but now let's take a look at part
Gary,
2
about
of the
20 minutes, okay, 15 minutes.
Sure, this is going to be a short presentation, only have a few slides. So this is a continuation of Nazar's excellent presentation last time on impact of oscillator noise on PTP time error, and I'd like to thank Nazar and also Jeff Gao for helping create this presentation. So first, for the agenda, we'll pick up where we left off last time by reviewing the key points, and then we'll give a brief demo of a PTP time error video, and those are going to illustrate those key points, and we'll conclude by showing a TCXO architecture that addresses these key points in order to create a solution that's optimized for synchronization applications. So in part 1, Nazar presented a model for IEEE 1588 servo loop that disciplines a local oscillator to incoming timestamps from an IP network. The model uses a PLL architecture where the local oscillator acts as the VCO that drives a local PTP clock that outputs time to the local system. And the bottom diagram here is a useful model that Nazar presented to illustrate the various contributions to time error. Starting from the left, the incoming network noise is low pass filtered by the servo loop bandwidth. And as this bandwidth reduces, more network noise gets removed, and that's good. So you might ask, why not remove more network noise by lowering the bandwidth even further? And it turns out that because of where the local oscillator sits in the loop, the local oscillator's noise gets high pass filtered by the PLL, as shown on the right side of the diagram. Thus, as the servo loop bandwidth reduces, it's going to filter more input noise, but at the expense of adding more noise from the local oscillator. And at some point, the local oscillator noise is going to dominate. So the local oscillator noise limits how low you can set the PLL bandwidth. And quieter oscillators allow you to set the PLL bandwidth lower to filter more of the packet timing noise and provide more accurate timestamps as a result. So that leads us naturally to what makes a quieter oscillator. And one critical factor that Nazar covered last time is the oscillator's ability to maintain a constant output frequency in the presence of thermal gradients. We call this phenomena frequency over temperature slope and abbreviate it as DFDT. And it's the measure of the change in frequency with change in temperature in units of ppb per degree C. And an ideal curve would be a horizontal line centered at 0 on the y-axis, meaning that the output frequency doesn't change with temperature. But in practice, of course, DFDT is not 0. And when evaluating a precision oscillator, the most advertised specification is frequency over temperature stability in units of ppm. And people just sometimes refer to that as stability because it's so common. For example, people will talk about a 1 ppm oscillator or a 0.5 ppm or 100 ppb. This is the frequency over temperature stability, and it's the first thing people typically think of when selecting a precision oscillator. However, because in PTP applications, the local oscillator is disciplined to the network timing, any frequency changes in the oscillator that are slower than the servo's update rate get filtered by the servo loop because the oscillator is high pass filtered. Thus, an oscillator's frequency over temperature spec, which is guaranteed over the lifetime of the oscillator, isn't really a critical parameter here. What is critical is the short-term stability resulting from changes in temperature. And by short-term, I mean the time between servo loop updates, because that stability will be seen immediately at the output. So looking at the graph here, the better oscillator is the one that has a more gradual slope, which is not necessarily the one that has less peak-to-peak variation on the stability axis or the y-axis. And so for these plots, the 100 ppb device is actually better, and it's plotted that way essentially to prove that point. So there's a video that I encourage you to watch on YouTube, and it's linked here, that compares the stability performance of a Quartz 50 ppb device on the left with a 100 ppb MEMS device on the right in the presence of airflow using a fan initially, and then a thermal gradient from a heat gun. And the MEMS device has 2 times worse stability on paper. It's 100 ppb versus 50 ppb, but it does have better DFDT. And the MEMS device also has much less thermal lag between its resonator and its corresponding temperature sensor compared to the Quartz device. And these 2 effects combine to improve performance for the MEMS device, as you can see in these plots. But in the interest of time, I'm going to skip this video in favor of a different video that creates a P2P network with 2 slave clocks locked to the same upstream P2P master and plots the time error resulting from changes in their thermal environments. The principles are exactly the same as the last slide, but I'm just going to show this video here because it's within the context of P2P time error.
Gary, if you can go back to slides.
Okay. This one?
Yeah, so actually you're presenting here like, no, the one with the fan, with the blower, with the,
this one here.
Yeah, so it might seems like a weird situation where you come with a blower and change the temperature, but in data centers, this is an actual event. When an operational engineer opened the rack for maintenance, the temperature goes up. It's not similar to any climate change which happens slowly. Data centers do have spikes.
And by the way, oscillators do respond to acoustic noise as well. I have seen often controlled oscillators that were affected by just the noise created by a fan.
Yeah, vibration can also have an impact, although I'm not talking about it specifically here, but yes, vibration as well. Yeah, we've seen cases where people have a rack where they kind of baffle, because some of the racks kind of have a baffle in the front, and that'll impact the way that the temperature flows through the rest of the chassis and create kind of strange effects. Was there any other comment or you wanted to make on that? Yeah. Should I show the video next? Yes. Okay. So let me go ahead and show that. This is a very short video. I think you can see it. Let me know if not. I'm going to start it, and I've put it. It's at an advanced speed here. So let me start again so I can sort of narrate it. So this is looking at our TCXO performance for 1588, and the first thing is that we have this. Pause it. So we have 2 boards. One of them has a Quartz device on the left, and one has a MEMS TCXO on the right. They each have fans in front, which we're going to turn on in the video, and they're locked to an upstream master in a P2P network. And we're looking at the frequency through a frequency counter, and we're going to integrate the frequency change to get to phase and convert that to time. So on the left board we have Quartz, on the right we have
yeah, actually,
MEMS
Gary,
device.
I think in this specific demo, we have compared exactly PPS signals from the master, grandmaster, and the slave card. So it shows you the exact measurement of difference in PPS timing.
Okay, thank you for that. And so here we're seeing the time error on the y-axis, on the left for the Quartz, on the right for the MEMS. And you're going to see the fans turn on, which they just did. And on the left side, you see the reaction in the frequency change and then the time error for the Quartz-based device, and then the MEMS-based device doesn't really change. And in a minute, you're going to see a hand reach in and show a hair dryer blowing on the Quartz device. Okay, so the fans stop now, and here comes the hair dryer. It's on a low setting at first, so it's just a little bit of heat, and you can see the deviation in the time error that causes on the Quartz device, and now it's shining on the MEMS device, and there's really not too much change. And next, we're going to switch it from the low-speed hairdryer to the high-speed, and so you're going to see a greater deviation on the Quartz side, and on the MEMS side, it's not going to change much. And the Quartz takes some time to stabilize, and that's because of the lag between where the temperature is sensed and where it should be sensed in a Quartz device. And so this video plays out.
The left one is Stratum 3.
You're asking about the stability of the left one?
Yeah.
Do you recall that one, Zara? I don't recall. This video is a couple of years old.
So the parts are the same as in your slide. So the left part is the 50 ppb Quartz TCXO, and the right side is 100 ppb frequency stability MEMS device. So those are technically better than Stratum 3 because Stratum 3 is like 250 ppb.
Okay.
Okay, so that's a kind of illustration of the physics. And now I want to try to explain why we're seeing these results. So where we want to sense temperature in the Quartz device is on the Quartz itself, but the sensor is located physically separate and below the Quartz. And this is going to create a thermal lag that we observed in the thermal gradients. In addition, the way the correction is applied, the device can only track very slow temperature changes. On the contrast, on the right side, the two MEMS resonators are created on the same silicon die right next to each other. The top resonator is designed to provide a very stable timing reference with temperature changes, whereas the bottom resonator is designed as a temperature sensor. So you want it to have a very wide frequency response with changes in temperatures. In fact, the temperature sensor we've designed here is the most accurate temperature sensor ever made in silicon. And both MEMS resonators sit right next to each other on a tiny silicon die. So if there's any change in temperature across the top resonator, it's measured across the bottom resonator as well. And this signal is used to correct the output frequency for changes in temperature. And this is how it gets integrated into the architecture. The top resonator drives a FRAC NPLL. The top resonator frequency never changes. I mean, not intentionally. It drives the FRAC PLL in order to synthesize the desired output frequency within a range of 1 megahertz to 220 megahertz. And frequencies from both resonators are fed into a temperature to digital converter circuit that's used by the PLL to compensate for changes in temperature. Because of where the temperature correction signal gets injected in the PLL loop, which is specifically in the feedback divider, the loop is able to track changes in temperature 40 times faster than Quartz devices. And that relates to the good performance that we saw in the video. So in conclusion, the take home, yeah.
Hey, this is Chris McCormick from Epson. Can I clarify quickly? It seems that the advantage that you're showing, if I'm summarizing you correctly, is due to the compensation circuit and the location of the temperature sensor, but not an inherent weakness of Quartz. Would I be summarizing you correctly there?
Yes, that's what I'm trying to illustrate is the physics that led to the better results. In this architecture with the Quartz, that's what we're seeing. If there's other architectures, then of course, I mean, it all relates back to the physics of it. Does that help you, Chris?
Yeah, thanks for the clarification. I'd say historically, there's been some poor choices made in terms of the compensation and temperature sensor location with respect to the resonator. And as a Quartz vendor, that's not something that's inherent to Quartz itself. So there are improved designs from what is being shown in this presentation. Just wanted to clarify. Thanks.
Okay. All right, so in conclusion, the real take-home point is that you can't judge a PTP performance by a precision oscillator's banner specification over temperature spec alone. The frequency slope over temperature, or the DFDT, is your system, that plus your system's temperature profile both greatly influence the maximum observed time error. Stated in a different way, oscillators with the same frequency over temperature stability can have significantly different DFDT performance, and thus PTP time error. So we presented this dual MEMS TCL architecture that we designed to be optimized for synchronization applications, including PTP, And the last thing I'd like to mention is that for applications that need to steer oscillators, we'd recommend using digital control rather than traditional voltage control, because digital control can fine-tune the servo loops with steps of up to 5 parts per trillion, or down to 5 parts per trillion, and eliminate board noise from having any influence on the control signal. So those
and
are
DAC resolution as well.
Sorry, could you repeat that?
And you're not limited by DAC resolution, which might be a problem. So Gary, if I may add, typically all of the oscillators, the precision oscillators, the way they're specified in datasheet is targeted for telecom boxes with very stable environment. And what we've seen is a characteristic of oscillator defined for temperature ramps not faster than 0.5 degrees C per minute or 1 degree C per minute, which is a fairly slow temperature change. And it, of course, doesn't take into account scenarios where you, let's say, open the enclosure for maintenance, or if you have to physically collocate your oscillator with the high power ICs that might start generating a lot of heat, like applications processor or something else. And what I would recommend is when you're evaluating new oscillator, just blast it with the heat, with the hair dryer, with the heat gun, warm up the board quickly, see what it does in those conditions, and then you will have a better intuitive understanding if conditions in your design will be actually acceptable for this device or not. Because, I mean, we can be talking a lot about theory and architecture to give you better understanding what are the challenges that we are facing as the vendors. But this is a very simple test that can just show you the performance very easily. So that's, I wanted just to add that.
That's a good point. Are there any questions, comments?
Yeah, Gary, do you see any benefit for that technology in the telco edge environment? I mean, when you don't have such major temperature fluctuation, is there any advantage?
Yeah, there still are advantages, and you will have some temperature drift, so that will be a portion of it. And there you're trying to get to a much finer, like you know, tens of nanoseconds rather than, you know, microseconds. And so
Right.
the stability of the device, the DFDT in particular, as well as the Allen deviation, we didn't talk about that here, but the lower the Allen deviation, the lower your short-term stability. Those all have implications in order to get down in the tens of nanoseconds.
Thank you.
If there are no further questions, let's change topic again. Any last comments? Thank you very much, Gary and team, for sharing today. I'll take control over the screen. Are you able to see my screen?
Yes.
All right, perfect. So sharing that on the second week of November, there is going to be an overall OCP Tech Week in which TAP, our incubation project, is going to get a half-day slot on Thursday of that week. And for that, we're looking to you all and to help in either presenting, creating the material, and participating in our panels. What we want to have is pretty much written here. This is a draft, of course. We are very open to get your feedback on it. So we were thinking to utilize our 4-hour time slot in a way that we start off with the whole question of why are we here and why are we looking to have data centers synchronized, and where precision timing and the whole effort of our precision timing is going to benefit data centers in the near future. And then tie it together with the synergies that we have with the other OCP community, whether it's the server group or the network group and the different sub-projects that are all going to be, I guess, part of this ecosystem or time appliances. We're planning some lightning talks about the two that we come up with were hardware timestamping revolution. So what that is going to generate in our environment, and then share from the hack that NVIDIA and Facebook had about measurement and testing challenges in the data center. Testing time, of course, measurement of time. We'll give a TAP workstream contribution overview. So we'll go through the 3 streams that we have, the work streams that we have. We did a good job today on the open source Grandmaster, and we'll have more. And then also on the APIs, software APIs, and the data center PTP profile. And then, of course, a demo. There's going to be a hands-on demo with the capturing the progress we had in the different work streams and the hacks we conducted around open source Grandmaster and the error-bound measurements. And we'll finish off with a panel. In the panel, we plan to have as many as possible entities, operators, vendors, and we'll come up with a good moderator to drive a meaningful discussion. So that's on a nutshell how we plan to spend the 4 hours. And again, if you guys think we are missing anything and you want to participate in or to contribute or own any of these portions, then this is a great opportunity to hear you. Comments, anyone? Ahmed, no one is asking any questions, so maybe you want to add your 2 cents about it.
Yeah, like make sure I want to make sure like everyone knows where the mute button is. Maybe we'll give you another 10 seconds. So I mean, like we really like most of these topics we bring in here is more like we're trying to encourage everyone to come together. I mean, if it was just our own ideas, we're okay, we're good in our own silo. But the reason why we brought it in here is like we want to hear these discussions, like all this excitement and everything. Like we have the contribution from the community. So I mean, it's starting like, let's say, from applications, like going down, like basically on both streams, like on the how and the why. We want to always keep the balance between the two. I mean, I always say this to my team: there is good engineering versus engineering for good. So, like good engineering, you make all these cool things, like probably you've seen that useless machines, like you press the button and then the hand comes in, turns it off. We don't want to build that. We want to build, like literally want to have like engineering for good. And that's why the how is always an important thing. Like we always remind ourselves on the how, the why, while we basically strive for the how. Yeah, Elad, let's continue with basically what more details we have.
I do want to say that this project is a multidiscipline one. We have software in many levels. We have hardware. We have chip design. We have analog design. We do encourage you to reach out to your colleagues at your organization and enlighten them that this project exists. Share with them what you learned. Just like 10 minutes or so. Maybe they will be interested. We are asking for more participants to join in.
So anyone from the OCP, from the Open Compute, would like to share a few words about the OCP Tech Week? Bill, are you still on?
Bill may not be on, but this is Archana.
Hey, Archana.
Hi, everyone. So just a couple of things. You are right. It is a half a day on November 12th. And I believe, if I am not mistaken, the time is from 8 a.m. Pacific to 12 a.m. Pacific. So just an FYI there. it's going to be about 4 hours, and so you'll have plenty of time there to do all of this. The second thing that I just wanted to say is registration will be available on September 1st. You can get more details on registration on our website. So this particular Tech Week event is available on the OCP website under events. So if you go to the OCP website, you should be able to get it. Get access to, the schedule. We'll be putting the schedule up here shortly, and we'll start registration. There is a call for participation, but it's only for selected tracks. I think the TAP group felt like they organically had so much content already for this 4-hour slot that they didn't want to really broadcast it to the other communities just yet. That doesn't mean that no one else can attend it, absolutely. And if you do have topics, then please discuss them with Ahmed and Elad, as they will be maintaining the agenda for the track. There are some very small sponsorship opportunities. We were just trying to make the event a lot of fun, so we are having things like coffee break sponsors and lunch sponsors and a Healthy Mind and Healthy Body sponsors.
There is no coffee.
Virtual coffee.
We'll send you the coffee, Dotan.
Yeah, that's exactly what it is. They're actually gift cards that our sponsors are providing to you to go and grab a cup of coffee. You might not have enough time to race over there and do that, but at least you can enjoy it later on in the day, at the expense of our sponsors. So it is it is a new platform we're experimenting with. It's different from the Virtual Summit. The Virtual Summit platform, we received feedback that it was just a little too editorial in some ways. It felt more like a classroom setting with dissertations and tutorials and things like that. So this is going to be very similar to the call that we just had for 1 hour, except it's going to be for 4 hours. It will be recorded. It will support video. We are right now deciding whether we want to do Zoom or GoToMeeting as our platform of choice. But it's supposed to be really interactive, and that was one of the feedbacks that we received from our virtual summit, was that there wasn't enough time for conversation. It was a lot of really good content, but just not a lot of time for conversation. So we've kind of gone 180 on this and made it completely interactive, assuming that folks that wanted to have content can come to our weekly calls here and get the technical content. But this is supposed to be a very technical deep dive. So that's all I had. If you have any questions about sponsoring, or if you have any questions about the broader agenda in general, feel free to reach out to me.
Thank you, Archana. Elad, let's continue with the 2 more slides, perhaps.
Sure. Okay, so an update about our work streams. So we combined together 2 work streams. Initially, we were thinking about the Grandmaster and going into 2 different avenues, or anyway, the presentation Oleg provided today is covering the work stream, the combined work stream for open source Grandmaster, which is targeted for both data center and edge use cases. And then the 2 other work streams, which we will reveal in the next meetings, are about the PTP profile and the software APIs, which are led by Michelle and Georgie. And stay tuned for that. The last slide is really just procedures and all the links.
So one more thing quickly I want to add to that, to the work streams. Like we had some interest, like Gary, if you're interested in some, I don't know, I had someone from Epson. If you guys are interested to have, let's say, a work stream on different oscillators or the discussion panels or something, please come forward and we can definitely integrate that. Like, it would be great to have something as that low level, because like we are designing things like considering like a full stack, like all the way from physics all the way down to software, or up to software.
Up to software, up.
For sure, up to software.
Okay, sounds good.
Okay. Thank you,
Wonderful.
everyone.
Thank you, everyone.
Bye-bye.
Stay healthy
Thank
and
you.
safe.
Thank
Just
you.
Thank you.
hey, Gary.
Yep.
Thank
Yeah, I
you.
want to mention that your presentation, as well as the one you posted from previous, has confidential in the footer there, and this is all open.
Oh,
so
yeah.
hope you're not actually presenting any confidential
No,
information.
I will send you new ones with it removed. That's just
Thanks
part
for
of
the
our
reminder,
standard.
David.
Yeah, good call.
Thank you, everyone.
Bye-bye.
Thanks, everybody.
Bye-bye.